All right, so here we go. Limits and an introduction to calculus, chapter 11. So in this first section, we have the introduction to limits. So what we're going to do is understand the limit concept, use definition of a limit to estimate limits, determine whether limits of functions exist, and use properties to evaluate limits. So you will need your calculators for a few of these because we're going to potentially be looking at graphs and tables to decide what the limit is. So here's your formal definition of a limit. If you have a function and it becomes arbitrarily close, so infinitely close to a unique number L, as x approaches some value from either side, then the limit as x approaches that value is L, where L is really your y value. And so this is how it's written here, is the limit as x approaches c, so c is some value on the x-axis of a function equals L. So c is an x value, and L is a y value. All right. So here's our example. We're going to use a table to estimate the limit as x approaches 2 of 3x minus 2. So in your calculators, go to your mode and put it back into function mode. And type in 3x minus 2. And so when we look at our table, we have an x value and we have a y value. And if we're approaching 2, then in your table set, we want to start at 2. But we want our change in table, let's go 0.001. So we would have, when we look at our table, if we were to look at it, we would have like 1.998. And then we would have 1.999. And then we would have 2. And then you'd have 2.001 and 2.002. So we're getting really close on either side of 2. And if you look at your table, your y value is 3.994. Then it goes to 3.997. At 2, we're actually at 4. And then we go 4.003 and 4.006. Right, and so if we ended up with even more numbers, if you started to look at the patterns, you would say as our x values get closer and closer to 2 coming in from the left, our y values are getting closer and closer to 4, right? Same thing here, as we come in from the right, your y values were above 4, but now they're going down. And this one, because this 3x minus 2, because that's a continuous function, and you actually have that value. So when x is 2, your y value is 4, then we would be able to say then that the limit as x approaches 2 of our function, that is 3x minus 2, the limit would be 4. So as your x values approach from the left and the right, your y values are both getting closer and closer to 4. All right, so moving on. This next one, using a graphing utility, or use a graph utility to estimate the limit. So here's what I want you to do. In your y equals, you are going, so in your y1, you're going to graph in a parenthesis for your numerator, x cubed minus 2x squared plus 2x minus 4, close that parenthesis, and then divide that by x minus 2, and put that in a parenthesis as well. All right, so as we look at this graph, most likely you see that we have a parabola that looks like this, right? But we're looking for the limit as x approaches 2. So what you could do is in your calculator, if you go to second calc value and you want to know when x equals 2 and hit enter, the issue here is it tells you that y, it doesn't have a value, right? And that's because you have a hole in your graph at 2, even though your calculator doesn't show it. There's not a vertical asymptote, but there's just a hole. So that doesn't actually have a value. So what that means is that at 2, so let's say that this is where we have 2. So on your calculator, in here you would have this little hole in your graph at 2, somewhere in here. So what you're going to need to do then, if we're not doing this algebraically, is go back into your table. And when you look at your table at 2, you should see that there's an error. But when you look at those values around 2, you can kind of make a pretty good guess as to where that hole is at 2, right? So if we were to come up with what that table was, right, and we were to write down our table to potentially help support our guess, we could say at 1.998, our y value is 5.992. And then at 1.999, we're at 5.996. At 2, we have an error, which means the actual value of the function doesn't exist, so it's not a continuous function, but the limit can still exist because your graph can approach from both directions, even if that actual value doesn't exist. And then at 2.001, we were at 6.004. And then at 2.002, we were at 6.008. And so when you start to look at the patterns, this 5 is getting increasingly close to 6. There's an error at 2, and then all of a sudden it jumps to just a little bit above 6. So you could probably make a pretty reasonable guess that the limit as x approaches 2 of this function would be 6, which means that this hole right here in your graph would be at the point 2, 6. The x coordinate's 2 because that's what it was approaching, and the y coordinate of the hole is 6, and that's what the limit is. That means your left and right hand sides of the graph. Like if you were thinking about this as train tracks, if the train was coming in from this direction and the hole was the station, it would get to the station here. And if the train was coming in from this direction, it would get to that same station. And that same station is at the point when y is 6. And that's the idea of the limit. If you come in from both directions to the exact same point, that's your limit, whether it's a hole or it's a closed circle. All right. So let's use a graph to find the limit here. So what we're going to do is we're going to graph this, and your calculator is probably not going to help you a whole lot because this is a piecewise function. So when we're graphing this, again, remember these are your y values. So y equals 1 and y equals -2. But y equals 1 when x does not equal 5. And then y equals -2 only when x is 5. So what we can pull from here is that we have the point -2, 5. There's just that one instance when y is going to be -2. So if we plot the point -2, 5, that's that second part. The first part says y is always going to be 1 except for at that point. So at that point up here, you're going to have a hole in your graph. And then otherwise, your y value is going to be 1. So it's going to be this horizontal line. And the question is, what is the limit as x approaches 5 of the function? So again, we have to think about, as we're coming in from the left and right, what is that y coordinate of the station that the two tracks are approaching? So this train track, if you were coming in from the left, what's the y coordinate of this station right here? 1. And if we were coming in from the right, does that y coordinate approach the same value? Yeah, so our limit would be 1. So something that will trick people is that when you have the hole right here and the point down here, they'll still pick the point. But again, if you think about the trains approaching the station, if there are no tracks into that point, the limit will never be that point. You've got to be able to get there from both directions. All right, limits that fail to exist. Okay, so this is your mean girls. Remember, when the limit doesn't approach anything, then the limit does not exist. So 3 ways that a limit will not exist. The first way is that they approach different numbers from the left and the right. So again, if we're in that idea of a train station, this first one would look something, you get piecewise functions, we'll have it, where let's say half of your function looks like this, and then the other half of your function looks like this. Right, so if you were coming in on the train from the left, you would be coming into this station. And if your friend was coming in from the train on the train from the right, they would be coming into this station, which isn't the same one. So when you approach two different y values, the limit doesn't exist at that point. The function increases or decreases without bound. So this just means that you're going towards positive or negative infinity. That usually occurs when you have a vertical asymptote. All right. And then the last way that it could potentially not exist is that if your function oscillates between two fixed values. And so we're going to actually look at a graph of all three of these, but this oscillating one is kind of interesting. So first one, let's compare left and right hand behavior. So this first example here says show that the limit does not exist. So showing the limit doesn't exist means we need to actually draw a graph to show that it doesn't exist. And so if you needed to graph this, let's say you don't have your calculator available to you, because like in calculus, you won't for the majority of what you do. Let's make a table of values and see if we can come up with what this pattern will look like. Now, first you can ask yourself, what does x over x simplify to? 1. So there's probably going to be some theme of 1 in here, right? So let's start picking some values, but we know that at 0, it's going to be undefined because you can't divide by 0. Right? So x equals 0 is kind of maybe like our middle number. So let's start at negative 2. And if you plugged a negative 2 in for x into the numerator, the absolute value of negative 2 is 2. And then if you divide by negative 2, you get negative 1. Does that make sense? Because for that first one, if we have the absolute value of negative 2 over negative 2, then that would mean that we get 2 over negative 2, which is negative 1. So our y would be negative 1. Same thing. If you plugged in negative 1, same thing happens. You get negative 1. At 0, it's undefined. And then if you plug in a positive 1, you get 1. Positive 2, you get 2. 1. Positive 2, you get 1. So when you graph this, as you're approaching 0 from the left, it doesn't actually equal 0, but your y value is always negative 1. And if you're coming in from the right, it doesn't ever equal 1, but it's always 1. So you would have open circles on that y-axis. So the limit doesn't exist because that left and right hand limit don't approach the same number. So this is kind of like that first reason why they wouldn't exist. The second one, discuss the existence of the limit. So on your calculators, I want you to graph 1 over x to the 4th. All right, so our graph, when you graphed it, looks like this. So the idea is that if you were on a train and your train was coming in from the left, all of a sudden your train just keeps going to the north and it never stops. Same thing over here, it just keeps going, but it never actually stops. There's not a station that it's going to approach. So we would say for this one that the limit does not exist. Now this can be a little bit confusing because sometimes it will say discuss the behavior of the function. And if we were discussing the behavior of the function, the behavior, we would say that we still use limits, But we would say that the behavior of the function as x approaches infinite or 0 is infinity. So the idea of your function can behave in a certain way, it's going towards infinity, but the actual limit doesn't exist. So you have to be careful about how they're phrasing the question. Are they just looking for that behavior, or are they actually asking you to determine what the limit is? All right, next one, oscillating behaviors. So in your calculators, I want you to graph the cosine of 1 over x squared, and then just do a zoom trig. So zoom trig is zoom 7.
Wait, what?
Right, and when you graph it, you get something that kind of looks like this. Right, it kind of looks like that. Right? What I want you to do now is go to zoom and just go to zoom in and hit enter. And hit enter again. So now we're zooming in. And you get something that's like, all of a sudden now you have even more lines. Right? So now all of a sudden you have a graph and you have even more lines. All right, so here on this one then, we would say that this does not exist because you can't actually approach a value. Right? We're not going to actually approach the value when it just continues to oscillate more and more. All right, we're going into the properties of limits. That was like all we were supposed to do for our day one. Oh yeah, sorry. All right, so this second part, I actually enjoy the second part a little bit more because this isn't so much just looking at graphs and tables. This is a little bit more algebraic. The idea of a well-behaved function where you have polynomials and rational functions with non-zero denominators. So continuous polynomial and rational functions. The first thing that you should try to do whenever you have to find a limit is to plug in that x value and see if you get a defined number. If you get a number, then that's your limit. It means it's a continuous function and it's just a point on the graph. So here the idea, some basic limits are if you have the limit as x approaches c of b is just a constant. So if you have a horizontal line, the limit will always be whatever the value is of that horizontal line. If you have the line y equals x, then whatever x is approaching will also be the value of that limit, right? Because if we were to plug a c in, if you have x to the n, when you plug a c in for x, you get c to the n. Or if you're taking the nth root of x, you can just plug a c in, whatever that value is that you're approaching. These are all just continuous functions with the idea that you're plugging in the x value that we're looking at on our graphs. And then you have some more properties here. So the idea is if you know what the limit of a function is as x is approaching a value, so if x approaches some value and you want to do b times that function, just take whatever the limit of the function is and then multiply it by the scalar. You can add limits together, you can multiply, you can divide, and you can raise them to a power. So we have 6 quick examples here. So the idea here is, if we look at A, if we want the limit as x approaches 4 of x squared, we're just going to say 4 squared. We're going to plug the 4 in for the x value, and we get 16, right? Because x squared is just a polynomial, so you're really just finding the y coordinate of that polynomial. The limit as x approaches 9 of the square root of 9. So you have to think, what would the graph of the square root of 9 look like? That's just a horizontal line, which means the limit at any approach on that horizontal line will just be whatever that constant is. This is B, sorry. For 5x, when x approaches 4, we just do 5 times 4. And you get 20. For E, we're going to plug pi in wherever we have x. So we're going to have pi times the cosine of pi. Cosine of pi is -1. So your limit is negative pi. For C, we plug in a pi, so we have the tangent of pi over pi. Tangent of pi is 0, so you get 0 over pi, which just gives you 0. And then for F, we would have 3 plus 4 squared. So you would have 7 squared, which would give you 49.